Hello, everyone. Welcome to today's session. My name is Wycliffe. Have you ever wondered or have you ever wanted to track atmospheric water vapor over your field of interest, maybe month by month using satellite data? This we can do simply in R or using Google Earth Engine and R interface or R program. We can monitor how much water column we have above our field. This is an important thing because it can help us tell the rate or water loss or transpiration or water stress from our farms, because this is an important factor which then determines how much yield or production we can get from our farm. All right, so in this video, we are diving into a powerful workflow that uses R, Google Earth Engine, and Sentinel-2 data to extract and visualize monthly water vapor pressure. We will draw a polygon around our field of interest, and then make an interactive map, and from where we will process full year of data with cloud masking and create both beautiful time series graph and interactive map. So stick around, and by the end of this tutorial, you'll be able to run this entire analysis yourself. All right, so let's get started. I will turn to R Studio because this series of videos are based in R Studio. Okay, so we'll start by loading the libraries. So the first library is RGEE, and then after loading RGE, we load map edit. This is the library which helps us to draw polygons or points or lines while on the RStudio side. You may already know that we have this drawing toolbox, toolbars, which we can use to draw polygons or something like that in Google Earth Engine. But we can do the same in R using map edit, basically the same. Okay, so map edit, and then we will need dplyr to wrangle the data. We will also need tidyr to clean the data after obtaining it from Google Earth Engine, and then we can visualize it using ggplot2. All right, so let us start by initializing our Google Earth Engine session. So that we do it initialize, and then we set drive to true, even though we will not be using it. So that was not very necessary. Okay. So we'll start by drawing our site of interest, and we will use draw features. As I already said, we'll use draw features from map edit, and then the feature we get, we'll need to create a column in it. So we'll mutate a column named name, and then that name, we'll assign it a value of name1, and then we select only that name. All right. So when we run that, a mapping area is created on which we can set the satellite background, and then decide on where we want to draw our polygon. All right. So I will pick this polygon and then come here, draw a feature around this area like that, and then finish at that point and click done. All right, so we have site. If I clear this, if we check site, it should be a simple feature collection, which is a polygon having only name and the geometry. Otherwise, it will be having field ID and some other attributes that we don't want. So I've just gone ahead and selected name only. All right. So after that, we can convert this our site to an Earth Engine object just by saying site, and then we pass it to SF as EE. That is coming from RG package. All right. So let's get our images. The first image we will get is the Sentinel-2 image. So Sentinel-2 image we get from EE image collection, $ image collection, and then $ dataset, and then Copernicus S to SR harmonized. All right. And then we will use, because we know this image has got a cloud cover, we need a cloud CS plus, we need cloud score plus image collection, which we then use to mask out cloudy pixels, right? So we don't use a threshold in this. We just use a cloudy pixel to mask out. We just use this Google Cloud Score Plus to mask out cloudy pixels, right? Because if we have some clouds in some regions, then they give different value in the image that are not actually what's on the ground. So we have to handle them. All right. So after getting the CS plus, we can then also set the date, because I said we want to do this for time series over several months. We can have our start date set. So we will start on 2024, January 1st, and then our end date will be, our end date will be on 2025, 01/01 exclusive. That means the end date is not included in the analysis or in the extraction of images. All right. So the next thing we are going to do is to start filtering our Sentinel-2 images, right? So we start by filtering bounds, filter bounds, and we filter bounds using site at engine. Okay. After filtering bound, we can filter date. So we filter date with start date, from start date to end date, right? After filtering for the date, we then go ahead and link our collection, because this is the collection which has got an image or a band which can help us to remove cloud. And that band is called CS band. All right. And then we map a function. So the function we are mapping takes one image. After taking an image, it picks a quality assessment band, which is from the image we select CS, right? After selecting the CS, we then get our image. And this our image is the original image, but with mask, with cloudy pixels masked out. So we update mask using QA, but only where that QA is greater than 0.6. All right, so after that, we then copy the image properties. So the image we are returning, $sign, we copy properties because we want to have time, time data or start time, so that we can do the time series for or the mapping over several months and retain that attribute on a month. So we pass that as a list, and this list is from system time start, right? This should be in quotation marks because it's an attribute. All right, so after that, we just pick the band of our interest. So let me go back to Google Earth Engine. If you look at Sentinel-2 bands, Sentinel-2 SR bands, you will realize that they are band 1, 2, 3, 4, 5, 8, 8, 9, 11, 12, all those. But then there is also WVP. This is the water vapor pressure band, which tells us the height of the water would occupy if the vapor were condensed into liquid and spread evenly across the column. So that is, if water vapor above this field from the ground surface until the top of atmosphere were to be condensed into a liquid and spread on this surface, how many centimeters will it occupy? Okay, so we will get that by using select function, and then we say water vapor pressure, because that's the band of our interest. All right, so after getting the water vapor pressure band, we then need to map this over months. So we will create a list of months, which is from Earth Engine list. We pick sequence, we create a sequence of months from 1 to month 12, right? So this month now is an Earth Engine list. So how do we then get the monthly water vapor pressure? We get the monthly water vapor pressure by mapping on this month. We map a function, right? So the function we are mapping, we'll get it from Python. So we use the EE-utils-py function, and then we provide it a function which takes 1 month, right? And if after taking this month, it converts it to an Earth Engine number. So we say Earth Engine $ number, and then M. So after getting the Earth Engine, then we pick a single image. And this image comes from, or we create an image from our Sentinel-2. So this we filter using Earth Engine filter because we are going to use an attribute or a property. So we filter using calendar range because already we kept system time start. So we have this calendar information, and then we pick from the beginning of the month to the end of the month using the month column. After that, the next step is to then get the median for this period, right? So that is the median image for 1 month, and then we multiply it by a scaling factor. So if we go back to this interface and check these images or the bands, we will realize that, let me open it here. We will realize that in water vapor pressure band, we need to multiply it by a scale of 0.001 under scale. The other bands are 3 zeros. For the water vapor, it's just 2 zeros. That helps us to convert the values to centimeters, which is therefore the depth of water, the depth that water vapor, if condensed into liquid, would occupy over our column. All right. But then after that, we know that Earth Engine normally index bands differently. So we need to change the band names. So we can create a variable called band names, which is a string. And this string, we can then call it water vapor pressure like that. And then we add the month number. So for that month number, it can come as a float or a float variable or a double. So for us to convert it to integer, we must format it like that. All right. So what then do? We use our image, but then we select the vapor pressure band, which we need, which is water vapor pressure. And then we rename it, right? So we rename it to the names that we have created, which is called band name. All right. And then we can also set it the month so that we know which month it's coming from. All right. As simple as that, we have monthly water vapor pressure. But you remember, we were using a list of several months. We were using a list of 12 months. So what we need to do is to convert this list of images into an image collection. To do that, we can say monthly image collection gets Earth Engine image collection, yeah, but then the image collection is coming from images in a list. So we use from images, and then we provide the monthly water vapor pressure, this one here. We'll just copy it and paste it here, all right? There is a problem. So that is the typo here. Now it is fine. Okay. So after getting the image collection, we need to convert it to bands. Why are we converting it to bands? Because actually, if I run this, you can see it's an Earth Engine image collection. Let me expand this. It's an Earth Engine object, which is an image collection. But we cannot do a reduction on this image collection easily. So the best way is to convert it into bands. So that one we just say monthly image collection. Very simple, monthly image collection, and then to bands. So that already converts our image collection into an image of bands. Control Enter, you find that it's now an image, not image collection, just by using two bands, okay, function. After that, we now have our image in as bands. So what can we do? We can easily do the extraction. So we can say our statistics will be monthly bands, and then reduce region. So we use reduce region, or we can even use reduce regions because we have a feature collection, and then the reducer is at engine $ reducer $ because this is a function to do, or a variable of drought stress. We'll pick the least, the driest pixel value. Okay, so we reduce it with the minimum. Then for the collection, we will pick site at engine because that is the our feature collection which we used, and then we scale. We set the scale to 10. Right. So those are the major attributes that we are interested in here. Well, of course, there are other things like CRS transform tile, maximum pixel per region, but our region is very small and those are sufficient. All right. So we have our statistics as a feature collection at engine feature collection, right? But for us to use it simply in R, we need to convert that feature collection into an SF object. So we have water vapor pressure as an SF being the statistic, but we pass it to Earth Engine as SF, like that. Very simple. I think this is one of the functions that I really love in this package of RGE, because with feature collection, we cannot do direct analysis using dplyr. So we need to bring it down to a simple features, and then we convert it to data frame. We don't have to export anything. We don't need to download anything to our Google Drive. Just by doing this, using this, we already convert our Earth Engine feature collection into a simple feature like that. So we have the water vapor pressure values for each month from January all the way to December for our field 1, which we digitized. All right, but it's still an SF object. So we can convert it to a data frame by saying water vapor pressure SF, and then SF function package, then we use st drop geometry. So that drops the geometry, and what we now have is a regular data frame, right? But this regular data frame is in wide format, so we need to convert it to a long format by saying df. We will use water vapor pressure data frame, and then we pivot it longer, right? So that one comes from tidyr. Okay, so the columns, we will get them from everything in this data frame, which starts with x. You can see all the variables start with x, except the field name. Okay, so this will give us, sorry, the field, the variable, the columns that we want to pick. And then where do names go? So names too, we say we want the names to go to month, for example, and then we want the values which are inside this month to go to water vapor pressure. So just like that. So if you run this, we'll see that the wide format has been converted to a long format, right? From the first month to the 12th month. And then we have the water vapor pressure values and the month values. But these month values don't look so nice. So we have to do a mutation to clean them, all right? So we'll say mutate a column, and this column, first of all, is called month. For the column called month, we will convert it to integer because currently they are characters, and then we substitute, we will substitute the water vapor pressure. We will substitute everything, uh, everything which is before water vapor pressure, just like that. Water vapor pressure, that's how we called it, water vapor pressure. And then after water vapor pressure, we remove everything. We keep just the number, right? So we use the escape key, and then we say D plus. This is a regular expression which we are using from the base R statistical or base R understanding, right? So this is why it's important not only to know the Google Earth engine itself, but also by under the working of the R programming language, how we can substitute, or we can use a regular expression to substitute these digits that appear before, after. We eliminate all this that appear before, and then we keep only the numbers, and then we pick that from the month column. All right, then we can also add a month label so that we have months as Jan, Feb, like that. So we'll use month abbreviation, which is automatically available in R, and then we get this from month. And then the levels for that factor will be the month abbreviation, right? Just like that. Okay, so if you check our DF, it is now as a clean data frame, which even though we are seeing this as numbers, but they are variables with factor labels mutated. Okay, sorry, month label was not shown. Sorry for that. Yeah, month label is January, November, if it is 11, 12 is December, up to the last one. Okay, so once we have that, we can therefore make a plot, which a simple plot using ggplot, and then we say ggplot, and then we provide our data frame. Let me see the head of the data frame so that I can clearly see the variables that I'm playing around with. Okay, so I can see that in the aesthetic, I will put the X on the X-axis, I will put the month label, right? So because that is what I want to be on the X, and then on the Y, we have the NDVI values, right? So not NDVI, but WVP, water vapor pressure. Okay, so go back here. On the y-axis, we want water vapor pressure values, and then we group by the name. We group by the name of the field, and also we color by the name, because we only have one field in this case, so the color will be, if we had several fields, then that would give different color for different names. Because this is time series, it's preferable to use geometry as the plotting, or the geometry for plotting. Okay, then we need to add geom point. This will put dots or points at the joints of each or at the points of each intersection of X and Y axis. Okay, we can use scale color brewer if we want. Then we provide a palette which is a bit green, and this is normally given by dark 2. It's a bit dark green because we are talking about T fields. Okay. Then for the labels, we will provide the map, the plot with the title, and we can say monthly water vapor pressure, right? Water vapor pressure for field 1, right? We can provide such a title, and then we say on the x-axis, we want a month, because those are months. And then on the y-axis, we have the water vapor pressure. And as I said, the unit for that is centimeters. That is the height of water vapor if condensed to a liquid over that column of atmosphere. And then the color, we just provide a legend title, which is called field. All right, we can visualize our plot and look at that. That's our plot. Tells us how the water vapor pressure has been behaving over our field over time, from January all the way to December. In March, it was low. In April, it was highest, and then it started descending over time. So if there were some yield reductions or something like that, we can tell that it was because the water vapor pressure above our surface, it was partly contributed to the water vapor pressure above our field. All right, so the dim doesn't look so nice, so we can already use dim minimal, uh, and then we provide a base size of maybe 14. Okay, so that gives the image, that makes it look more clearer than before. Okay, so you can continue formatting it the way you want, adding colors and adding all that. But what did we notice? We noticed that in the month of March, there was a strong reduction in the water vapor pressure column. So this was quite dry period. And then we want to visualize those two images from our bands, right? We had monthly bands here. We can pick those the month for March or the band for March and also the band for April and compare them interactively. Okay, so first of all, we center our map around our site EE, right? And then we set zoom level to say 17. Okay, after setting our center, we can then use map add layer. Okay, and then the layer we add is monthly bands. Monthly bands. And from monthly band, we will only select 1 month. If you look at the band names of monthly bands, we can say monthly bands, $, band names. It's an Earth Engine list, so we can get information from it. Get info. And if we look at them, they start with 0 and then they end on at 11. That is the last one. So to pick the first one, we'll use this name. This is the second one, and this is the third one. And the fourth one is this. Okay. So let's select the third one, the third month, which is 2 underscore water vapor pressure underscore 3. And then we clip it to our region of interest. So we clip it to site EE, right? Site underscore EE. And then after that, we provide visualization parameters, which is vis params. Not sure why. We take the bands and then okay, so that should be outside this. Okay, we should close this one here. We select that and then we click to this. Then, yeah, like that. That is now correct. So visualization parameters, we provide a list in which we say the minimum is 1, because we can see the minimum here is just around 1. And then the maximum water vapor pressure deficit value, we can see it's around 3. So we can stretch the values up to 3. And then we provide a palette, which is the visualization or the colors that we want to stretch. We can start maybe from brown for the dry areas with low dry atmospheric column to maybe yellow, and then we end up with dark green. Okay, so That's the visualization parameters that we want for our month, for the month of interest. That is for the month of March. Okay, and we can see the month of March over our region of interest. We can see that it was quite dry. So we can also do this for the month, for the next month. So I will just copy this very fast and then change this to 3 and change this to 4 because that is the month of April. And when we run that and check the image, we see that in the month of April, it was quite green. So we can combine the two maps by using this bar here. It's not L, so that we can flip across easily. Okay. Okay, so we can compare the two maps. All right, so I will provide this background. Something happened. Okay, let me take this up, Control Z. Yeah, we need to start it from there and then we run. There is an error somewhere. Some brackets not necessary. No, it's important there. It's only that. Okay, something is not right. Let's see what it is. That one closes that, so we don't need this. And then this one does not close any, so we don't need it there. Okay, so we can run this. All right, so we have this image visualization which compares um, the two images. So on the left we have the month of April. On the right we have the water vapor pressure and within our field for the month of March. So we can see how dry the air was in the month of March and how wet or how much water vapor pressure we had during the month of April. These two tells you whether the plants suffered much water loss or evapotranspiration rate was probably higher in the month of March than in the month of April. So the plants basically recovered in the month of April. Why did I choose those 2 months? Because I saw the deepest drop was in March and then the highest gain was in April. So I just wanted to see these two contrasting periods and how they look like in our map. Okay, so I think this is useful for you. I hope you've enjoyed this the same way I've done. And there you have it. In just one script, we've gone from an empty map to a full analysis, drawing a field, loading and masking Sentinel-2 imagery, calculating monthly water vapor pressure composites, and creating both a static plot and interactive visualization, right? This fantastic foundation for any environmental monitoring project. You can easily adapt this code to analyze the or other spectral indices like NDVI or NDWI water index. So if you found this helpful, hit the like button, share it with a friend, and subscribe to the channel for more tutorials on R, geospatial analysis and remote sensing. Or the code is in the description of this video below, right? So you can find the code to this video in the description section. So you can reproduce it yourself. Thank you and enjoy coding.